Hi guys, good morning. In this video, we're going to see the problem minimize maximum of array. It is one of the problems in which the most optimal solution is much easier to write than the better solution. So yeah, it's up to you guys. In the end, please let me know which one of the approaches, for sure not the approach one, but the approach 2 or 3, which one was more intuitional for you. And the next question one is which one was more easy for you. So it's two different questions for you guys which you have to answer. You will see my answer in between also, but yeah, I'll go through via complete intuition step by step of entire thing from brute better to actually optimal. So yeah, let's start with the video. The problem says that we are having a zero indexed array called as nums comprising of n non-negative integers, which means all the integers are positive or zero. Cool. What is an operation like? An operation is that you must choose an integer I such that I is from 1 to n minus 1. Remember, you cannot choose the zeroth index. You can choose from 1 to n minus 1, which means that you can choose from starting from the index 1 up till the n minus 1. You can choose. What operation you can do is that you can decrease the, if you choose an index, let's say I, you can decrease the value of I and increase the value of I minus 1th value. It's the reason that we are not choosing the zeroth index, because there is no I minus 1 for that 0. Thus, operation what we can do is ith index I can decrease its value, and for I minus 1 I can increase its value. Okay, pretty cool. What is the result like? Result is that we need to return the minimum possible value of the maximum integer of nums. Firstly, this statement might also be confusing for you guys, but I'll explain. After performing any number of operations, so one thing I know that all this operation which is mentioned, which means we choose an ith index, I decrease its value, I increase the value of I minus 1 index value. So we can do this operation any number of times. Now what it says is that minimize the maximum integer of the nums. So at any point of time, whatsoever is the maximum value of this nums, at any point of time, whatsoever the maximum value of this nums, I just need to try to minimize that as much as possible at any point of time, which means ultimately whatsoever my array would look like, its maximum value should be as minimum as possible, which means okay, I can't go minimum than the maximum value which is allowed. Let's say example pretty quickly. With this you can just easily get to know what actually this particular statement means. It means that okay, at this point 3716, what is the maximum value? 7, right? I want to minimize it, so I will try to reduce it. So what I will do is I will reduce its value by 1. So I have to increase the I minus 1 indexed value by 1. So I increased it, I reduced it, it became 4616. Now the maximum value of this entire array is 6. Now again, let's try to reduce it. So I reduced it, I get a 5. I have to increase it, I get a 2. I reduced my 6, I get a 5. I have to increase the previous index, I get a 5. Now the current array is 5, 5, 2, 5. Now again, the maximum element of this array is 5. I'll try to again reduce it. So what I can do is I can reduce it, get a 4. I can increase it, get a 3. Okay, I can reduce it, get a 4. I can increase it, get a 6. Oh, get a 6. Earlier my maximum value was 5. Now because of next operation it became 6. It was not reducing, it increased. Thus I can easily say okay, after that it's just repeated because it just went kind of here that okay, now it's 6. So basically it's just that I just reduced it. It can be minimally reduced up till this point where the answer is 5, 5, 2, 5. And it's for sure understood also, right? Because 5, 5 is consecutive kind of. So if I increase this, so if I decrease this, so ultimately it has to increase. So if both are at the same level, if I reduce it, so other will increase. If I increase it, other will reduce. So it's kind of that it is the minimum which it both can be. So it is that okay, my 5 is my actual answer. Now first very beautiful solution which we can easily think, like these steps which we performed here, we can just use those steps to actually write the brute force. How? As simple as that. At every point of time I was just finding the maximum value. At any point of time, I was just finding the maximum value of this whole array, and I was just trying to reduce that. I just went on to this. I found, okay, what is the value, maximum value? It was 7. I tried to reduce it, increase its previous value. I got another array, 2, 6, 1, 6. Now again, 1, 6. Now again, I just went on to this array, find the maximum value. Okay, reduce it and increase it. So again, I am going to this array, which is operation of n. I go and look at the maximum value of this array. Cool. Then I just reduce the element and increase the element, which means if the value is, let's say, 8 and other value, let's say whatsoever is previous, so I just reduce it, let's say 7, I just increased it. So how many times I can reduce a value? Step by step, one by one. It is the maximum value of nums of I, which is nothing but 1e9. So in total, every time I go, I look at the array, I just grab the maximum element, I just reduced it. Every time I go, I just look at the array, grab the maximum element, I reduce it. So I have to do like reduce the element again and again. For again the whole array, I have to go and see, okay, what's happening for this array. Thus it is n into nums of I. Nums of I can go up to 1e9, so it is 1e14. Can you just imagine 1e14 as a complexity? This is fun, but still 1e14. This can't be possible. So yeah, let's optimize it. How? If we look at this operation, we are moving on the array and seeing, okay, I have this array, and at one point I have this particular I. So earlier in the brute force, what I was doing is I was just reducing it by 1, because I was not sure what could be the minimum value which it could reach. For example, in our case, it started from 7, then it moved to 6, and then it moved to 5. It was happening, right? I was moving step by step because I was not sure it could reach 5. What if I would just randomly try? Okay, randomly try for 6. Random try for 6. If 6 is possible, which means, okay, if 6 is possible, so I will just try for 5. If 6 is not possible, then for sure any value lower than 6 will also not be possible. I want to just see, I just wanted to minimize my particular answer. So if, let's say, as in this example itself, let's say I take 4, 3, 2, 1. So ultimately I will just try to reduce it. So from 7, I'll just try to reduce it to up till I just try to go back until it is going back. It was the operation which we were happening in brute force, right? Why not? I'll just try some random value, let's say 3. I tried a random value 3, and I'll just check anyhow. Let's say for now we don't know how we will check, but anyhow, if I can check, okay, is 3 as an answer is possible for me? If it is, then good, very good. If it is not, then one thing is for sure, right? No answer less than 3 will also be possible, because I just wanted to minimize it. Minimum element I took at 3, and it's also not possible. How come the minimum then that would be possible? So for sure it is not possible. So my range become bigger element. If it is possible, if my 3 is possible, then I'll just try. Okay, let's try for smaller values also. You remember something what's happening here? We have something as a range, we choose a random value, then we choose, okay, is possible or not? If it is possible, then I'm just moving on to its left range. If it is not possible, then I'm just ignoring the left range, I'm moving to the right range. You saw what happened. It is nothing but a binary search. So ultimately we know, okay, what is our range, which means we want to minimize, right? Ultimate result, its maximum value, it can be 7, which is the maximum value itself. Minimum value, it can go to up till 0. As I said, elements are non-negative integers, so it is the same thing. I'll just apply a binary search in this, which means I'll just show, I have also showed you guys how we just tried the minimum value. Try means I'll just try any value which is minimum, and I'll see if that value x, if it is possible, then very good. I'll just try to query to try. I'll just try for the smaller value than x. If that x is also not possible, then I'll just try, ignore the left part. Okay, Anything smaller than x is also not possible. I'll just try for the bigger part. It is how we can have that intuition. Okay, we had that array, we just trying, because we were just reducing the nums of I one by one because we were not sure at what point of time my nums of I it could go. Like I just reducing from 7 to 6 to 5 to 4, because I was not sure, because 5 could be minimum. So I was just reducing one by one, and I reached to a point. So rather than just reducing one by one, let's try to put a value and just try to see if it is possible or not. If it is, then you know how Boolean search works. Now, okay, you said, okay, Aryan, I will just try for some random value in this range 5, 4, 3, 2, 1, and I'll just see, okay, if it is possible or not. But how will you check if it is possible or not? Because we are applying operation like on the whole array itself about that value. Yeah, I'll do the exact same thing. What we were doing was, if we have, firstly, we can't apply the operation on the first element, so let's remove it. If we have the second element, B, I have marked it as A, B, C, D, E. Let's see how. If we reduce it, we get B to B minus 1, A to A plus 1. For sure, because we can just reduce this element, increase this element, and we can apply this operation any number of times, right? So in one step, I can just get a B minus 1 and a A plus 1. You will agree on that part? If I have this C and I want to apply operation on C, I can just reduce my C and increase my B. Also, if you clearly look, your C is reduced. Your C is reduced, but if you apply the same operation on your C, now your new A and B are A and B plus 1. You apply the same operation on A and B plus 1. So B plus 1 will reduce by 1, it will get a B, and A will increase by 1, it will get a A plus 1. So ultimately, I can also say that I can also get A plus 1 and C minus 1 in 2 operations, which means to reduce to C, I'm not necessarily required to reduce only to increase only the previous element. I can increase previous to previous element also. Something clicked your mind. Yes. If I have this D, then I can increase the previous element. I can also increase the previous to previous element, as we saw here. I can also increase the previous to previous element, which means for some index I can choose to increase any of those previous indexes I want. That's a big catch for this problem. How? For this index, to reduce this index, I can increase any of these indexes as much as I want. It's just that I just want to reduce this index. What's happening in this is, if we have this E and I am wanting, and I just choose, let's say I just want to choose a random value, let's say X. I just choose a random value X. I wanted, okay, random value X, if it is possible or not. If this X as a minimum value possible or not, which means every element ultimately should be less than equal to X. It is what I wanted. So I'll just try to reduce this. So I just wanted to make it less than equal to X. What I can do is I can increase any of the previous elements. I can increase any of the previous elements, which means I can make them maximum up to X, which means all these can increase, but it can go up till maximum to X, which means all this can go and have a value less than equal to X. You saw one thing what happened. If I'm trying for X, I want, okay, I can basically decrease it. I can basically decrease it. I can basically increase it. I can basically decrease it. I can basically increase any of these as much as I want. But ultimately, every one should be less than equal to X. So I can easily say that, oh, A plus B plus C plus D should be everyone. As I said, A should be less than equal to X, B should be less than equal to X, C should be less than equal to X, D should be less than equal to X, E should be less than equal to X. So for sure there's some, because ultimately I'm decreasing it, increasing it. So in total, its sum should be less than equal to X for some particular I. That was such an amazing thing. That our prefix sum should be X into number of elements, because it's just repeating X, right? And X is like repeating how many times? That we have 5 elements, which means at the index I equal to 4, I have 5 elements. So it is just that I plus 1 into X, which means that X is X plus X plus X 5 times. This is such a great condition, that my prefix sum, if it is less than equal to I plus 1, prefix sum should be less than equal to x into number of times it has occurred so far, which means I plus 1. This is a condition we can choose to check, okay, if my x is a valid mid or not. As I said, I'll just try for some mid and I'll just see in this particular array, okay, if it is possible or not, if it is possible or not. To check if it is possible or not, I'll just iterate on this whole array for every I. I'll just see, okay, if my x should satisfy this condition, which means prefix of I should be less than equal to I plus 1 into x. So it should satisfy. If it is satisfying, I'm good. For every I, it should. If for any I, it is not satisfying, I'm screwed up. X can't be possible. I have to try for some larger value, let's say x plus 1. But x can't be possible, that's for sure. It is how our binary search will work. Firstly, very simple. We choose a left. See how we choose a left and a right. I have told the exact same thing in our binary search video. It is the most important. In this, we generalized, okay, any code of binary search we can write in this form. Exact same code I have written in this video, because we will write the same code for binary search in every problem. It's just that we will change only one condition, which is this one. Exactly same code for every case. In this video also I told, okay, how we choose the left and the right. It is the answer. What is the answer? How the answer can be left or right, which means what is the minimum value of answer, what is the maximum value of answer. Minimum value of answer is nothing but 0. As the numbers can be non-negative. Maximum value of answer, it can be the maximum value in that particular nums array, right? Cool. How we choose our is valid condition? We just have, as I said, I just need to make sure that my prefix sum at any point of time, it should be less than equal to I plus 1 into x. So I just have a prefix sum here for every I. I just check if my prefix sum is more than this particular condition, x into I plus 1. I want it less than equal to for every I. If it is more, I need to return a false. But for every I, if it is being considered, okay, if it is less than equal to, ultimately I can return a true. It is how our binary search would work. You saw what happened. We just tried to reduce from brute force, and we knew, okay, we have this n, we have this nums of I, and we are moving nums of I one by one, rather than we can just, because we are decreasing one by one, rather than we can just choose a random index and just see if it is possible or not, and then maybe we can just ignore the range so that we don't have to go one by one in this nums of I. Thus the complexity is nothing but n into, now we are iterating on this whole nums of I, right? I just split it, which means at every point of time this nums of I, which means the whole range, which means from 0 to 1e9, it will just be splitted half every time. So it's nothing but log of nums of I, and nums of I just choose the maximum. Although we can just say, okay, my nums of I maximum value is 1e9, so it is just like nothing but n into log of 1e9. Space is nothing but O of n, because I am choosing, space is O of 1, because I'm not choosing any array to actually store this particular thing. So it was the better solution. You thought, oh, Aryan, it looks super optimal to us. No. If you clearly look at this condition right here, can you infer something from this condition? Okay, like before that, let's see what happened and how we can optimize it. So if we use the same concept which was mentioned above, like legit same, just thinking in some reverse way, what was happening was, when I said I have to choose this particular element, when I had to reduce this complexity, because I had this brute force solution in mind, when I had to reduce the complexity, I had one thing in mind. Either I can directly choose the minimum value which is possible, because see, I was reducing from 5 to 6 to 7 to 6 to 5 to 4 to 3, like this. So one thing I can say, okay, one thing I am linearly going to my optimal value. Let's say my optimal value is this, which means the minimum value which is possible is this. So one way is I linearly go. One way is I go by binary search, which means in log n step I just choose this. After that I choose this. One step is I directly go to this. Why not? It's possible. Just let me know why not I can choose this minimum value x directly. But how, Aryan? How I will know the minimum value x directly? This is the most optimal solution that we just get to know the minimum value of x, which means, see, x is nothing but the minimum value which we take directly. How directly? If we just go and see the same condition which we wrote above, prefix of sum, like prefix sum of I is less than equal to I plus 1 into x. We just wanted this x, right? It's a minimum value, and we just wanted this x. Earlier I was trying for every x, like I was just having a mid, and then I was trying, okay, if this x is possible or not. Rather, why not I just choose this x out itself, which means I just choose this x out and just say prefix of I upon I plus 1 should be more than x, which means for every I, if I go and find, okay, my prefix of I upon I plus 1, let's say it is 1, it should be less than equal to x. For here, let's say my prefix of I upon I plus 1, let's say it is 3, it should be less than equal to x. Let's say I am at I equal to 2, I just say, okay, if my prefix of I upon I plus 1, let's say it's 2, it's less than equal to x. So basically, I'll just go for it at every value, and I know I need to find the minimum value. My x is what? Minimum value. So which means, okay, I'll just try, okay, this x is minimum, x is minimum, x is minimum, but I want to satisfy this whole array. So my x should be here. So basically my prefix of sum of I plus 1, prefix sum of I upon I plus 1, it is less than equal to x, and I want to minimize my x. And I for sure know it will start from prefix of I plus upon I plus 1 and it will go on further. It will increase. Its minimum value is this particular value. So I know it, okay, it's a minimum value, but it's a minimum value for what? For particular I. So I just need to grab every I and I'll just check, okay, it's a value, it's a value, it's a value, it's a value, it's a value. And I just need to make sure my whole array is satisfied with this condition. So I just grabbed a maximum value out of this, which is 3, let's say in this case. And ultimately my 3 is for sure more than equal to, more than equal to, more than equal to. And also it's satisfied the condition that it is minimum possible for this entire array. Because ultimately I was saying that my x should be more than equal to 3. It's the same thing which we had to do in this question, that I just know my x, it should be more than equal to this condition. So it is the minimum benchmark I can have. And I just need to go to every I to actually find out, okay, what's the maximum I can choose. What's the maximum I have to choose. So I just go on and find, okay, what's the maximum in this particular whole array for this value of prefix of I upon I plus 1. I do the same thing. I find the prefix sum. I just, at every step, I just find prefix sum of I upon I plus 1. And as we know that we have to take a ceil value, so I just grabbed a ceil value. And in the last video, people were saying about the concept of this, like I just use the same concept. If you want to find the ceil, so one thing you can do is ceil of a upon n, but here you have to make sure that you have to convert the number into double, at least one number to a double, at least, else it will not work. But if you want to do the integer division of the same ceil thing, then you can just use a plus n minus 1 upon n. It will give me the ceil value. So ultimately, I'll just do a prefix sum of the same thing, ceil. I just get I plus 1 minus 1, and I'll just get a sum plus I. And ultimately, I just get this max value. For every I, I'm just grabbing, okay, x should be more than equal to 3, x should be more than equal to 1, x should be more than equal to 2, x should be more than equal to 4. X should be more than equal to 6, x should be more than equal to 5, x should be more than equal to 3. Ultimately, my x should be, for this entire array, it should be more than equal to 6 and more than equal to 6. So minimum value it can have is 6. Thus, I can just return that minimum value which is possible. Here, I'm just grabbing for every index, but ultimately, I'm just choosing this is the minimum value possible. And I have to choose for every index, so I just need to grab the maximum for everyone. Thus, ultimately, its complexity is O of n and space is O of 1. And yeah, every code for C++, better solution I have provided, and also the optimal solution for every language I have provided. So if yes, then yeah, you're good to go. Although the problem can be explained in just 5 minutes if I just have went through this particular condition and have showed you that, okay, x you can get, and it's easily possible to have prefix of I upon I plus 1 and you're good to go. But I purposely went through brute force. From brute force, we just grabbed the possible ways to improve that, because in interview you have to say to the interviewer how you went, how you reached to the solution, and not how you got the answer. Okay, like it's O of n, but how you reached here, it's more important than how you actually solved it. So yeah, it's the reason I just went from the brute force. In the brute force, we just knew, okay, it is happening. How we can just reduce that linear complexity? We just use a binary search to actually reduce that. From that binary search, when we were solving that, we just found a condition which can actually help us to actually solve it in the linear time also. So yeah, it's all from me, and I hope that you guys liked it. Yeah, especially to let me know in the comments that what was more easier for you, intuition wise and also solving wise. And from me, for sure, intuition wise was more of a binary search, but solving wise was more of a linear one, which means this O of n1, last one which you saw. And yeah, that's all from me. I took a very long time for this problem. It was just a 5 minutes problem, but yeah, I think it was worth it. It's all from me, and I hope that you guys liked it. If yes, then do hit the like button. It helps me, motivates a lot. And yeah, share with your fellow friends, juniors. We're also having a graph series, BAP graph series, which is going on. If you want to check, you can just easily go and check that. And yeah, that's all from me. See you in another. Goodbye, take care.